All right, chemistry. This is your video lecture, first part of your two-part video lecture for Chapter 2 and 3 because we are combining sections. We're combining section 2 and 3 into one. And take heart because this will be the last section that you go through in this course. Hooray! All right, objectives for this video lecture. Define and give general equations for synthesis, decomposition, single displacement, and double displacement reactions. Now there are 4 listed there, but we're also going to be adding the combustion reaction into that list right there. Second bullet: classify a reaction as synthesis, decomposition, single displacement, double displacement, or combustion. Okay, there's your combustion. So we have 5 different types of chemical reactions that we are going to be looking at in section 2. Then list 3 types of synthesis reactions and 6 kinds of decomposition reactions. Now, before you start freaking out about these different types of synthesis reactions, single displacement and double displacement, the main rub here is going to be identifying them as synthesis, as decomposition, as single displacement, as double displacement, or as combustion reactions. Once you've done that, coming up with 3 examples of synthesis or coming up with 3 examples of decomposition is actually going to become fairly simple. So don't put the cart before the horse. Then list 4 kinds of single displacement reactions and 3 kinds of double displacement reactions. Same idea there. Focus on the general equation for each of those types of reactions, and then the examples, the 4 examples and the 3 examples, they'll come nice and easy. And lastly, predict the products of a simple reaction given the reactants. All right, let's get started. Now, there are several ways to classify chemical reactions, not just these 5 that we have here. There are many more. Any way you slice it, there are way more than 5 different types of reactions, but we're going to look at 5 main types here. The classification scheme described in this section provides an introduction to 5 basic types of reactions: synthesis, decomposition, single displacement, and double displacement, as well as combustion reactions. Let's start with the synthesis reaction. In a synthesis reaction, also known as a composition, and we're gonna see that this is the opposite direction from a decomposition. Okay, synthesis is the opposite of decomposition, so that's why it makes sense for a synthesis to also be known as composition. Composition is the opposite of decomposition. So in a synthesis reaction, 2 or more substances combine to form a new compound. This type of reaction is represented by the following general equation. Here's your general equation for a synthesis reaction. We have whatever stuff A. This might be monatomic, it might be polyatomic, I don't know, but it's going to be this substance A and this substance X, and they come together to form one thing. Okay, they come together to form one thing. Now, it's not to say that there might be some second product over here. It's not a 2 things become one thing. There may be a second thing over here on the product side, but it is that at some point there's a combination of A and X here. Okay, and like I said, A and X can be elements or compounds. AX is a compound for sure because it's going to be a combination of, at the very least, elements. All right, robot lady has something for us.
Carbon dioxide and water can react to form sugar and oxygen. This is an example of a synthesis reaction. 2 substances have combined to form a new compound, sugar.
All right. Now we're going to get into these few kinds of synthesis reactions that you're going to need to be able to list. Okay, and list is very, very simple. You don't have to explain it, don't have to describe it, just list these things. Now, if you get a single element and combine it with oxygen, you get an oxide. These names should already be familiar with them, or familiar for you. almost all metals react with oxygen to form oxides. So here we have an example. Here's an example, a metal, magnesium, reacting with oxygen. Remember, oxygen is a diatomic molecule, Brinkelhoff, so it's O2. And so I'd have a balanced chemical equation. Over here we have MgO. Okay, two things, A and X, coming together to form AX. Group 2 elements react in a similar manner, forming oxides with the formula MO, M representing the metal, and Mg is a group 2. Okay, so it has a +2 charge to balance out the oxygen's -2 charge, so that's why there's simply one of each. That's why we have MO, one metal, one oxygen. All right, that was group 2, magnesium in group 2. Let's look at a group 1 oxide, lithium, having a +1 charge. You're going to need 2 lithiums to balance out the -2 charge from the oxide. Now, group 1 and group 2 elements react similarly with sulfur. Okay, not just oxides, but in the same way we have an MO or an M2O. We're going to have a MS or an M2S. Instead of oxides, we call these sulfides. And down here at the bottom, we have 2 examples of items down in group 1, rubidium and barium from group 2, reacting to form sulfides. We have rubidium sulfide and we have barium sulfide. Again, making sure that those are ionically balanced, you're good to go. Now, we can also have a synthesis reaction between nonmetals. That's totally okay. We have been looking at metals and nonmetals. It can happen between 2 nonmetals. That's fine. For example, we have sulfur and oxygen here. You probably heard of sulfur dioxide. Again, it's simply the combination of sulfur and oxygen to form one compound. We also see it in water. You saw this reaction happen in the movie The Martian with Matt Damon. We have hydrogen coming together with oxygen to form water. We also have not just oxygen or sulfur. You can also react metals with halogens. Okay? Most metals react with group 17. That's the halogens. The halogens to form ionic or covalent compounds. Group 1 metals react with halogens to form ionic compounds with the formula Mx. Okay? Again, that's group 1, so that's going to be +1 charges when they form an ion. Halogens, group 17, that's going to give me -1 charge, so you just need one of each in order to balance ionically. And so that formula is Mx, where M is the metal and X is the halogen. An easy example is salt, NaCl. Okay, we have sodium combining with a chlorine gas here, in Cl2, to form NaCl. That's a group 1 metal and a halogen. Group 2 metals also are going to combine with the halogens in the exact same way. It's just now we're going to need 2 of the halogens. So the general formula is going to be Mx2, right? Because that group 2 metal is going to have a +2 charge. You're going to need 2 halogens in order to balance that out. Now, fluorine is so reactive that it combines with almost all metals. So that's a good one to use in your examples as far as creating your list of examples for synthesis reactions. Active metals, which is something we'll talk about in section 3 more specifically, but I think you can get the idea right now. Active metals are highly reactive metals. We say that they're active. Oxides of active metals react with water to produce metal hydroxides. For example, calcium oxide, okay, CaO, is going to react with water to form hydroxide. Now, calcium is a fairly active metal. And so calcium oxide, being the oxide of an active metal, will react with water to produce a metal hydroxide. So instead of being calcium oxide, the result, the product is calcium hydroxide, according to the example here. Continuing on with synthesis, our last slide on synthesis reactions. Many oxides of nonmetals in the upper right portion of the periodic table react with water to produce oxyacids. Remember, oxyacids is an acid that contains oxygen. For example, we have sulfur dioxide in water. Okay, again, you're going to create sulfur dioxide by a synthesis reaction. But if you then react that sulfur dioxide with water, you're going to get an acid, specifically an oxyacid. In this example, this is going to be sulfurous acid, because that's a sulfite. Certain metal oxides and non-metal oxides react with each other in a synthesis to form salts. For example, at the bottom here we have calcium oxide and sulfur dioxide. They're both oxides. You can form a salt, which basically is an ionic compound. Notice we have calcium from the left side. Sulfite is going to be polyatomic ion, all from the right side of the periodic table. Well, that's it for synthesis reactions. On to decomposition reactions. A decomposition reaction, a single compound undergoes a reaction that produces two or more simpler substances. That substance is being broken up. Okay, it's being broken up, it's being decomposed. Decomposition reactions are the opposite of synthesis reactions, right? Composition versus decomposition. They are represented by the following general equation. AX reacting to form A and X. AX is the compound. A and X can either be elements or individual compounds, but they're being broken apart. Now, there are several different types of decomposition. One of the kinds that we're going to look at specifically is called electrolysis. Electrolysis is the decomposition of a substance by an electric current. And so look at this. Look here at this general equation. We have our substance reacting and breaking down into two separate substances. But look what's over the reaction arrow, electricity. This is in the presence of electricity, this will happen. And so, if there is no electricity present, this reaction, this decomposition will not happen. Oxides of the less active metals, which are located in the lower center of the periodic table, decompose into their elements when heated. Again, decomposition. Notice this one substance breaking into multiple substances. And then look on top of the reaction arrow, you see the delta. Okay, heat. Heat is being added. Unless you heat these things, this decomposition won't happen. All right, robot lady, what do you got for us?
Electrolysis is the use of an electric current to cause an oxidation-reduction reaction. Electric current is the passage of electrons. Because oxidation is the loss of electrons and reduction is the gain of electrons, the passage of electric current through a solution causes these reactions. For example, when current is applied to water, the hydrogen in the water is reduced to elemental hydrogen, and the oxygen is oxidized to elemental oxygen. Because 2 moles of hydrogen are formed for every mole of oxygen, twice as much gas is formed in one tube as in the other. When the electricity is shut off, the reaction stops. Electrolysis is also used in electroplating.
Go down here. Come on, cursor. All right, thanks, robot lady. All right, some other examples of decomposition reactions. These are going to come at you pretty quick, so get your copying pants on. Decomposition of metal carbonates. Again, what's a carbonate? Oh, it's a CO3. How am I supposed to know that, Mr. Johnson? Look on your periodic table, because on the opposite side, there's a polyatomic ion sheet, of which carbonate is one. Decomposition of metal hydroxides and decomposition of metal chlorates. Okay, again, chlorate. Just look it up. Look it up. Polyatomic ion sheet. Notice for each of these, you're going to have to heat this substance in order to get it to decompose. And the last one, you actually need a catalyst. Okay, you need a catalyst as well. But notice on every single type of decomposition reaction, you have one substance breaking down into at least two different substances. There may be 3. It's a little bit more rare, but at least 2. Let's go decomposition of acids. Decomposition, you guessed it, you're going to have one thing breaking up into 2, okay? But we're just looking at an acid here. Now, certain acids decompose into nonmetal oxides in water. For example, carbonic acid is unstable and decomposes readily at room temperature to produce carbon dioxide and water. Notice we're breaking up that H2CO3 into CO2 and H2O. It's decomposing. Now, I will say this before we go any further. You're not going to have to memorize these things like certain acids decompose into nonmetal oxides in water. That's not the portion you're going to have to memorize. You're going to have to memorize the general concept behind decomposition, or the general concept behind synthesis. All right, we'll cover one more nice and quickly. Single displacement reactions. In a single displacement reaction, Again, don't skip over the words here. Displacement. Okay, displacement. Something's being displaced. How many things? One. Single displacement. Also known as a replacement. So if you hear me say single replacement, okay, that's what I'm talking about. It's the exact same thing. One element replaces a similar element in a compound. Many single displacement reactions take place in an aqueous solution. In fact, most of the ones we're going to look at are in aqueous solution. Single displacement reactions can be represented by the following general equations. Okay, we have A reacting with Bx to form Ax and B. Notice all that's happened is A has replaced, hint, hint, has replaced B to bond with X. Now, because B has been displaced, hint, hint, B is now by itself. Okay, B is now by itself. But it doesn't just happen with the first listed thing, the cation, the metal. It can happen with the nonmetal. Okay, Y here being a nonmetal can boot the X, which in this case is the nonmetal. But you're simply just replacing something similar to it. So that means a metal will replace a metal, and a nonmetal will replace a nonmetal. Oop, too fast. If we look at displacement of a metal in a compound by another metal, okay, again, looking at metals replacing metals, we're having aluminum here displace or replace lead. Okay, aluminum bumping out lead. So now aluminum is now bonded to the nitrate. If we look at displacement of hydrogen and water by a metal, okay, these highly active metals, like in group 1, react vigorously with water to produce metal hydroxides and hydrogen. Why? Because they're replacing the hydrogen in water. This sodium is very much more active than hydrogen and is booting it out really hard, really fast. That's why it reacts vigorously. Happens very easily. And so we're replacing one of the hydrogens with a sodium. Less active metals such as iron react with steam, okay, because that's where the energy is coming from, the hot steam, that's thermal energy, to form metal oxide and hydrogen gas. What is this iron replacing? This hydrogen. How can I tell? Because this hydrogen is all by itself. Why was it all by itself? It got booted. Displacement of hydrogen in an acid by a metal. The more active metals react with certain acidic solutions, such as hydrochloric acid and dilute sulfuric acid, replacing the hydrogen in the acid. Again, you're not going to have to remember all this text that I'm reading through. You're going to have to remember the general format of this reaction. What's happening? This lone substance is booting, is replacing the less active cation here. And in this case, I know hydrogen is a nonmetal. I get that. I know that. You know that. But compared to chlorine, it's acting like the metal. So the magnesium is going to replace the other metal, right? You're going to only replace similar things. And so the magnesium boots the hydrogen. Hydrogen ends up by itself. Magnesium ends up bonded to the chlorine. All right, last slide. Displacement of halogens. Now, fluorine being the most electronegative of all the halogens, I mean, not to mention the rest of the periodic table, is the most active halogen. And because it's the most active halogen, it's going to replace any other halogen if it gets the chance. So in group 17, each element can replace any element below it, okay, but not any element above it. And since fluorine is at the top, it gets to replace everything, right? Because there's nothing above it. There are only things below it. For example, if we react some chlorine gas with a KBr, this chlorine is above bromine on the periodic table, so it's more active. It'll replace it. Check it out. It's going to boot bromine. Fluorine, the very top halogen, is clearly more active than chlorine. It's going to boot the chlorine, so chlorine will be by itself. Fluorine will be with the sodium. But then when we look at bromine, if we mix some bromine with some potassium chloride, bromine is below chlorine on the periodic table, meaning it's less active, meaning it can't replace chlorine. And so there's simply no reaction. In that solution, we're going to continue to have bromine and potassium chloride. All right, chemistry, remember what's being asked of you. Don't focus on the parts of this presentation that aren't going to be asked of you. I know I threw a lot of words out there. You had to copy really quickly. But we're here to focus on the general concepts of these three reactions we've covered so far. We'll cover the double displacement and the combustion reactions next time. I will see you next period.